So please pay attention. Okay, so let's begin. Let's start with the story of Moonshine. So the story of Moonshine really begins at the classification of finite simple groups. Okay, so finite groups, hopefully you're all familiar with. Finite groups we all like and we think they're cool and we want to study them. Finite simple groups are basically what elements are to molecules. So finite simple groups to finite groups is the same thing as like atoms to molecules. So in order to study all finite groups, you might want to start by studying all finite simple groups. And again, in order to study something, one way of doing that is to classify them and then study the categories separately. So like write a periodic table. So the mathematician's version or a group theorist's version of a periodic table is this classification that took actually a really long time for mathematicians to figure out, and it's considered one of the greatest achievements of 20th century math. It is called the classification of finite simple groups, and it is a very clean, nice theorem that says the following. It says that all finite simple groups, almost all finite simple groups, fit neatly into three infinite families: cyclic groups, alternating groups, and finite groups of Lie type. There are 26 exceptions to this rule. There are 26 groups that don't fit into any of these families, and so they're like inherently interesting. These are called the sporadic simple groups, and there are 26 of them. And here is a picture that I stole from Wikipedia, basically. This is a Wikipedia picture of the sporadic simple groups. The nodes are groups, and then the lines are subquotient structure. Okay, so the one that we're going to talk about, the one that we're most interested in, is this one on the top. It is called the monster group. The monster group is the largest of the sporadic simple groups, and it has this order. So the order of the monster group is 2 to the 46 times 3 to the 20. I'm not going to read out this whole number, but it is this large number, which is about 8 times 10 to the 53 in scientific notation, I guess. The monster group was first conjectured to exist in 1973, and then it was first constructed in 1981. So there was a while between the first conjecture of the monster group and the first construction. I'm not going to give you many dates in this talk, but 1981 is interesting because later I will talk more about that. Okay, in the meantime, between 1973 and 81, we had a conjecture that such a group exists. And based on that conjecture, Conway and Norton, Conway of this seminar's title, that Conway, they conjectured that the smallest non-trivial irreducible representation of the monster group is 196883 dimensional. If you don't know what that means, I will tell you what a representation is in just a second. So Conway and Norton conjectured that the smallest non-trivial irreducible representation is 196883 dimensional, and Fisher, Livingstone, and Thorne computed a character table of the monster based on this assumption. Okay.
Excuse me,
yes.
Maryam. So this is the largest known finite simple group, right?
Is this the largest known finite simple group? No, it's not. So for example, you can find, that's a good question. Remember that Sn is the order of Sn, the symmetric group on n things, is just n factorial. So you can make arbitrary large finite groups as you want. Is it the largest known finite simple group? I also do not think so, because cyclic groups are simple. So like any z mod nz is simple. So pick n to be
particularly this is regarding to sporadic.
Yes, this is the largest sporadic simple group. And that is interesting. That in particular is interesting because it is a weirdly large number, like 8 times 10 to the 53 is a really large number, but then they stop. Like, so they go from like, a small number. So it is weird that that there are 26 groups that don't fit into the story, and then the largest one is this like strange large number. So yeah, so the monster group is mysterious. That is a completely fair thing to ask. Okay, so great. So let me take a detour and just give you a quick spiel on what a representation is and what a character table even is. Character table of the monster group is again going to be interesting in the story, so I want to spend some time here. If you already know what a character is, just bear with me for a second. So here's how we define the representation of a finite group. I'm going to let V be a finite dimensional vector space over C, and then a linear representation of a finite group is just a homomorphism from G to GLV. GLV is the general linear group of V, by which I mean these are maps from V to itself that are invertible. So if this is your first time looking at this definition, here's a simple example of a representation. You can take any element of G and you can map it to the identity map. So by identity map, I mean the map that maps any element of V to itself. So I'm basically taking elements of G and looking at them as maps of this vector space. If you like the language of actions of a finite group, then this is an action of the finite group on the vector space V. Okay, if I pick a basis for V, so V is just an n-dimensional vector space, I can pick any basis, then I actually get a matrix representation of G. So for the representation that I said, where you just map G to the identity map, a matrix representation would just be map G to the identity matrix, the n by n identity matrix, where n is the dimension of this vector space. Okay, so that's what a representation is. And here's my first example of this talk. I am not going to give you the answer, but if you get bored of listening to me talk, you should try to find all one-dimensional representations of C4, where C4 is the group on 4 elements, cyclic group on 4 elements. So this you might have also seen it as Z mod 4Z or something. Okay, so pausing here to see if there are any questions or concerns. Okay. If not, so here's one main theorem of representation theory, which says that every finite dimensional representation of a finite group G over C is either irreducible or decomposable into irreducible representations. So by irreducible representation, I mean that each of these, the only non-trivial sub-representations of these are 0 and W itself. And then I can pick any representation and I can write it as a direct sum of irreducible representations. So maybe it is useful to just look at irreducible representations of a finite group. Here's another invariant that I need to define. The character of a representation is the function chi from G to C, which is given by chi of G is just the trace of this matrix rho of G. Remember that trace of a matrix is invariant under base change. So it is independent of basis. So whatever basis you picked for your vector space, the trace is an invariance of the vector space. And also it is a class function, by which I mean that it's constant on conjugacy classes of the group. So remember that conjugacy classes, the conjugacy class of H is all elements that are of the form GHG inverse or G inverse HG. And since the trace is invariant under basis, trace of GHG inverse is actually just equal to trace of H. So this is from linear algebra. And this means that trace is character is an invariant of this representation. Okay, so now I'm ready to define what a character table is. So the character table of G is a table with entries chi I gj, so chi I rows and gj's are columns, where gj's are the conjugacy classes and chi i's are the irreducible representations of G. So here's my second example. So if you did the first example, you have possibly 4 representations of C4, and I'm gonna now give you the answer for the first example. So here's how you fill in a character table. So chi1 is the first irreducible representation. One possibility for a representation is just, map X to the identity map. Okay, so what are the other irreducible representations, one-dimensional irreducible representations of C4? Let's see, so what does that even mean? So if I want to compute G goes to GL1C, so 1 by 1 invertible matrices on the complex numbers. So what are 1 by 1 invertible matrices on the complex numbers? These are just complex numbers, but not 0, because that's not an invertible matrix, right? So that's what the representations of C4 are. So I need to find a number to map X to. What number should I map it to? What are my possibilities? Remember that X to the 4 is 1. So now my question to you guys is, can you tell me 4 numbers in 4 complex numbers, not including 0, such that if you take their 4th power, you get 1?
Plus minus 1, plus minus iota.
Good. Okay, so plus minus I, plus minus 1. So I can map X to 1 minus 1, I minus I, right? And then, I can figure out what happens to X squared and X cubed just by that. So if I take the square of 1, I get 1. If I take the cube of 1, I get 1. Minus 1 squared is 1, and so on. You can fill in the rest of this table. Very good. So this is what a character table is. So great. Now you can ask, I just told you what the one-dimensional representations are. Why haven't I filled out like the 2-dimensional, 4-dimensional, so on representations? Well, here's the other theorem, which says the character tables are square. So actually, as soon as I found 4, I know that those are all of them. So actually, C4 only has one-dimensional representations. This is a general theorem that Cn only has one-dimensional irreducible representations. But anyway, so character tables are square. So here, finally, now that you know what a character table is the character table of the monster group. So here. So first, disclaimer, the character table of the monster group was not going to fit on my slides. It's a really large group. It actually has 194 columns and 194 rows. So this goes on in both directions. So there's more rows and more columns. I'm just looking at the top left corner. Okay, and I will come back to, we will stare at this table again. So for now, it's just some numbers in front of you. But at this point, I'm going to take a detour in the story. So consider this as like a movie where the two main characters are eventually going to meet. So I've told you some background in the first main character, which is the monster group. My other main character is the J function. So I'm now going to take some time to tell you about the J function.
Excuse me, may I have a question?
Yes, please.
Okay, so you define the character table by the conjugacy classes. And in your example, I guess there is only just one conjugacy classes. Therefore, we have just one character table. Is the character table always unique?
The character table is unique, yes. Classes? Yes.
But how you can define, because there are different conjugacy classes in the group. It can happen.
I am not sure I completely understood your question. There are only, these are the 4 conjugacy classes of C4. So those are them.
So for example.
Yes.
Okay, but that's the conjugacy classes in this case are very, very trivial, just containing one element. Each conjugacy class contains just one element.
Yeah, so, great.
Yeah, so I'm thinking, suppose we have a group, we have non-trivial conjugacy classes, more than one element. What would be the character table in that case?
Yeah, so good. I think I understand your question. You're asking if there was if this conjugacy class had a different representative, would I get the same character table? And that is this thing that I said before. Let me go back to this. So remember when I said that characters are class functions? So characters character values don't change if you take a different representation data of your conjugacy class. So you can label your conjugacy class however you want, but the actual values don't change. So that's this fact that your character is a class function. Does that answer?
So this means that every group has a unique character table.
Yes.
Okay. Thank you.
Okay, thank you for that question. Yeah, so if you want like more details on why this is a class function, I'm just going to refer you back to the fact that trace of A, B, A inverse is just trace of B. So remember from like linear algebra, determinants behave very nicely. Determinant of AB is just determinant of A and determinant of B. But this is not true for the trace, but it behaves like almost very nicely. It behaves like this. So that's why, so this is just conjugates. So on conjugates, character tables, characters' values are the same. All right, other questions, comments, thoughts, worries, screams of agony? Okay, so let's now take a different route and look at the J function. So I'm going to start by defining what a modular function is. The J function is a modular function. So the group SL2Z, which is defined to be 2 by 2 matrices, A, B, C, D, where AD minus BC is 1, where these are all in A, D, B, and C are all integers, acts on the upper half plane, H, which is this stuff, which is tau in complex numbers, such as imaginary of tau is positive. So like literally the upper half plane, literally the stuff whose imaginary part is positive, if you look at complex plane as the plane. By tau goes to A tau plus B over C tau plus D. So again, if you get bored in my talk and you want another exercise, check this. Check that if I act on tau, so if I start by something that is in the upper half plane and I land at A tau plus B over C tau plus D, and I have this condition that AD minus BC is 1, then this also lands in upper half plane. So its imaginary part is also positive. Okay, so a modular function is just of level 1 is just a function that is invariant under this action. And I need some growth condition in order for this function to like not be too crazy. So this is kind of like saying, I want my function to be meromorphic, but don't worry too much about the growth condition. A modular function is just a function that is invariant under this action. And the J function, the elliptic modular invariant, is the simplest non-constant modular form in the sense that every other modular function is actually just a rational function in J. But the point here is that the J function has what we call a Q series, a Fourier series. So let me explain what this is. So notice that by definition, the element 1101 lives in SL2Z. So first, do we agree with this? Well, clearly 1 times 1 minus 0 times 1 is 1, so its trace is 1. If 1101 lives in SL2Z, then I want to know what the action of that is on tau. Well, the action is just tau plus 1 over 1, which is tau plus 1. So the J function is actually invariant under tau, periodic in tau. And if I define Q to be e to the 2 pi I tau, then this fact just means that I have a Fourier series, j tau equals q to the negative 1 plus so on. Okay, so now it's time for our two heroes to meet. I am going to write down on the same slide the Fourier series of the J function and the character table of the monster group. And I am going to pause here and I'm going to let you just look at the slide, meditate on the slide. Tell me if you notice something, any thoughts that come to mind are welcome.
I didn't pick that the power of Q, how the things are moving. So where is the constant term?
Oh, the constant term is just 0 in this case. For the J function, it is 0.
Can you explain a little bit about how these coefficients are appearing here?
How do you write a Q series? Yeah. Okay. So notice again that do you agree that 1101 is an SL2Z? And by that I mean that J of tau plus J of tau is equal to J of tau plus 1. Do you agree with this?
Okay.
Okay, so if something is invariant under tau and tau is in the upper half plane, basically what I'm saying is that you can write a Q series for something that behaves this way. So I haven't told you how to get these coefficients. I'm going to find a page here. Here's my page. But here's a quick explanation. So the upper half plane maps to the punctured disk D by tau goes to e to the 2 pi I tau, right? And then my functions, if I take a modular functions are functions from H to C. Okay, and now I'm saying there is a unique way of writing your modular function as a function of Q instead of tau, where Q is this. Instead of writing your modular function as f of tau, I can write it as f of Q. Okay, now in terms of Q, it is a meromorphic function, not holomorphic, but meromorphic. And for meromorphic functions in complex plane, you can write their Fourier expansions. You can write, if I have a function in terms of Q, I can always write Cn Q to the n, where n can be, negative infinity to positive infinity, but I really want it to be greater than like some number. So that's why I added the condition that like my function grows at most exponentially. So I want these to be Laurent series. Now, what are the CNs? Well, they will differ with each f, and I haven't told you and actually won't tell you how to find them for the J function. But this is just it is well-known thing that those are the coefficients for the J function. Does that answer your question? Does that at least?
Okay.
So these are just Fourier. So it's the same thing as like you write the sine function as its Fourier series. You write 3 factorial and 5 factorial. So in a similar way, you can find where 19684 comes from or 214. But yeah. Okay, great. So again, I'm going to pause here again on this slide. I really want people to make some conjectures. Tell me what they think is happening here. Are there any thoughts that come up are welcome at this point? Please, unmute yourself and answer, or put in the chat. Like, I'm happy to read the chat as well.
So the coefficient of Q is somehow, so the first number, second number, I guess. So there's some.
Who's talking? Please say.
Nakib.
So I'm Nakib. So okay. the coefficient of Q is somehow similar, almost just the difference of 1.
Yes, very good. Okay, perfect. So that is a very
maybe.
Go ahead.
Okay.
Go ahead.
I don't know. There are other connections. I don't know.
You said maybe, so you have another thought. Please tell me the other thought.
I have no other thought. The only link we can see here is that here the coefficient of Q is almost is the difference of 1 in the character table, in the first column of the character table. Yeah.
Okay, thank you, sir, very much. There's also someone who posted in the chat. Very good. So this is an audience full of John Mackay's. So yes, this is exactly right. let's see, let me find a highlighter that will show up. So this number, these two, it does show up. Okay, 19683 plus 1 is 19684, which is this number. Very good. So this is exactly what happened to John Mackay in 1970s. He was working with the monster group. Again, the monster group is not yet, we don't yet know if it exists in 1970s. He was working with this character table and he was like, oh, this number looks very much like this other number that I know. And the other number is the coefficient of the J function. He told this to John Thompson, and John Thompson noticed this other thing, which I was hoping that someone here will point out, is that if you actually add this number, the first three numbers together, so anyone who is like very quick at arithmetic, if you add these three numbers together, you actually get
Q square.
Very good. Good. Great. That is a very good observation. And if you were me, you would now be like, oh my God, what if the third number is the same as the sum of the first four? So let's add these four together and maybe this keeps going and we have found a pattern. Well, that fails. Okay, I'm not going to do the maths here, but I'm just going to do it mod 10. So look at it. Just look at 1366. 6 plus 6 is 12, plus 3 is 15, plus 1 is 16. So you should get a 6, but you get a 0. So that already fails. Again, if you were me, you would be like, all right, well, I give up. This was obviously a coincidence. Let's go home, right? But John Thompson said, well, actually, okay, they don't add up exactly like this, but they might add up if I like fudge them a little bit. So if you actually look at, let's see, 2 times 1 plus 2 times the second number plus 1 times the third number and 1 times the fourth number, and you add these together, you actually get this number. So again, I'm not going to do the arithmetic, but look at it now, again, mod 10. You get 6 plus 6, 12, plus 6, which is 18, plus 2, which is 20, so you get a 0. So at least it works, mod 10. Okay, so do the arithmetic. It actually turns out to be this number. And now there's hope that there's like more going on. But at this point, I'm going to consider the fact that I'm only looking at the first column of the character table, but the character table is really rich. It has other columns as well. So now let's look at other columns of the character table. So let's look at 2b. You can also do this with 2a, but I thought that you might think that I'm cheating if I'm just looking at the first two. So I'm just going to pick another random one. So let's look at 2b and do the following. I'm going to start writing down a function that I'm going to call t2b of tau. And I'm just going to use the j function as like a formula for t2b. So the j function is q to the minus 1 plus something times q, where the something is, remember, the sum of the first two entries. So I'm just now going to artificially like add the first two entries here and make this 276. Okay, then something times q squared, which is the sum of the first three entries, which now the third entry is negative. So you'll actually get negative 2048. Plus 2 times the first entry plus 2 times the second entry plus 1 times the third entry plus 1 times the fourth entry. And please check my math on this. Please actually really check my math on this. I've forgotten what the number is. I think it is 11202 q cubed plus order of q to the 4. Okay, so now I've just written down some numbers next to some q series. And you can ask, or is this function that I've written down, t2b, is this an interesting function by any chance? And actually it is. It is a well-known modular form. It is this one. It's these numbers are actually turn out to be a modular form. If you've taken any classes on modular form, if you've ever like seen anything on a first course in modular forms, delta of tau is kind of one of the first ones that you learn about. It's the smallest cusp form of weight 12 and so on. So T2B is another well-known modular form. And now, again, if you're a mathematician, you want to generalize. So you can ask, well, what about the other 192 columns? If I start doing this thing with every modular form, well, that's exactly what John Thompson conjectured. He said